Imagine for a moment gazing up at the night sky, not just as a casual observer, but as someone standing at the very edge of everything we know. Picture the inky blackness stretching infinitely, studded with countless stars and galaxies, each a distant sun, potentially hosting its own complex stories. Now consider that within this vast, awe-inspiring canvas, time itself might bend and twist, and space could stretch into dimensions we can barely conceive. This isn't just a flight of fancy. This is the real, captivating frontier of human understanding, a place where the familiar rules of our everyday lives dissolve into a profound and exhilarating mystery. Today, we're embarking on an extraordinary journey, not through a science fiction novel, but into the very fabric of our universe. We'll be exploring the boundaries of space and time, diving deep into theories that challenge every preconceived notion we hold about reality. Think about the most enigmatic phenomena in the cosmos, the crushing gravitational pull of black holes, where even light cannot escape, or the tantalizing possibility of wormholes, theoretical shortcuts through space-time that could connect distant corners of the universe in an instant. These aren't just abstract concepts for physicists in labs. They are fundamental elements of a cosmic drama playing out on a scale that dwarfs our wildest imaginations, constantly inviting us to question what lies beyond the limits of current scientific knowledge. From the faint echoes of the Big Bang to the potential existence of multiple universes, the questions are as vast and varied as the cosmos itself. This isn't merely a video about scientific facts. It's an invitation to expand your mind, to ponder the deepest questions that humanity has ever faced, and to connect with the sheer wonder of existence. We'll unravel some of the most compelling secrets hidden within the cosmos, discussing ideas that have captivated brilliant minds for centuries. What if time isn't a linear river flowing in one direction? Could there be dimensions beyond the three we perceive, shaping our reality in ways we can't yet grasp? Join us as we push the boundaries of human knowledge, venturing into the captivating unknown with an open mind and a spirit of discovery. Prepare to have your perspectives shifted and your curiosity ignited, because the universe is far stranger and more beautiful than you might ever have imagined, and understanding its mysteries is a journey truly worth taking. So, where do we begin this mind-bending journey? Our starting point has to be perhaps the most profound shift in our understanding of the cosmos. The realization that space and time are not separate, unyielding entities, but rather a single, dynamic fabric. This revolutionary idea came from none other than Albert Einstein, who, early in the 1900s, introduced his theory of relativity. Before Einstein, people generally thought of space as a fixed, three-dimensional stage where events unfolded, and time as a constant, ticking clock that applied equally to everyone, everywhere. It was a simple, intuitive picture that had worked for centuries, but Einstein changed everything. He proposed that space and time are inextricably linked, forming what we now call space-time. Imagine a giant, flexible sheet like a trampoline stretching out infinitely. Now, if you place a bowling ball on that trampoline, it creates a dip, a curve in the fabric. According to Einstein, massive objects in the universe, like planets, stars, and galaxies, do precisely the same thing to space-time. They aren't just sitting in space, they're actually warping the very fabric around them. This curvature is what we perceive as gravity. When smaller objects, like our Earth, orbit the Sun, they're not being pulled by some invisible force from afar. They're simply following the curves and dips in space-time created by the Sun's immense mass. It's like a marble rolling around the edge of that dip in the trampoline. This concept reshaped our entire understanding of the cosmos. It transformed gravity from a mysterious force acting at a distance to a geometric property of space-time itself. This wasn't merely a theoretical curiosity. It had profound, testable predictions. One of the most remarkable was the existence of gravitational waves. Think of these as ripples in the fabric of space-time, much like waves spreading out on a pond after a stone is dropped. Einstein predicted that incredibly violent cosmic events, such as the collision of two black holes or the explosion of massive stars, would send these ripples radiating across the universe at the speed of light. For decades, these gravitational waves remained purely theoretical, a testament to the elegance of Einstein's equations, but beyond our ability to detect. However, in the 21st century, with the development of incredibly sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, we finally, directly observed these elusive ripples from distant cosmic cataclysms. This groundbreaking discovery not only confirmed a century-old prediction, but also opened up an entirely new window onto the universe, allowing us to hear the cosmos in a way we never could before. It truly set the stage for modern astrophysics, allowing us to explore phenomena previously unimaginable. This brings us to one of the universe's most extreme manifestations of warped space-time, black holes. Imagine a cosmic vacuum cleaner, but instead of dust, it's sucking in light, matter, and even the very fabric of space and time itself. Black holes are regions where gravity is so incredibly intense that nothing, not even light, the fastest thing we know, can escape once it crosses a certain boundary. This boundary is famously known as the event horizon. Anything that passes this point is gone forever, swallowed into an infinitely dense point called a singularity within the black hole. Physicists often describe the singularity as a place where the laws of physics, as we understand them, completely break down. All the matter that falls into a black hole gets compressed into this unimaginably small, infinitely dense point. Think about that for a moment, an entire star, perhaps many times larger than our sun, crushed down to a size smaller than an atom. This extreme density is what creates such an overwhelming gravitational pull. The space-time around a black hole is not just curved, it's twisted and stretched to an astonishing degree, forming a kind of one-way cosmic trap. For decades, black holes were largely theoretical, existing as elegant solutions to Einstein's equations. Scientists had compelling evidence for their existence, observing their gravitational effects on nearby stars and gas, but directly seeing one was considered impossible because, by definition, they emit no light. However, that changed dramatically in 2019 with the groundbreaking release of the first ever image of a black hole's event horizon. This wasn't a photograph in the traditional sense, but an image constructed from radio wave data collected by a global network of telescopes called the Event Horizon Telescope. It showed a bright, glowing ring of superheated gas swirling around a dark central, void the shadow of the black hole known as M87 star. This incredible achievement provided direct visual confirmation of these enigmatic giants and offered a tantalizing glimpse into a region of space-time previously only imagined. The observation of M87 star marked a monumental step forward, bringing these once mythical objects from the realm of science fiction squarely into the realm of observable reality. But even with images, black holes continue to challenge our understanding. What happens inside that singularity? Could they be gateways to other universes, or perhaps shortcuts through space and time? These are some of the most profound questions that black holes force us to confront. Some theories even propose that black holes might be connected to wormholes, hypothetical tunnels through space-time that could theoretically allow for interstellar travel or even time travel. While purely speculative, the extreme warping of space-time around black holes makes them a focal point for exploring the very limits of possibility within our universe. They represent the ultimate cosmic laboratories for testing the boundaries of Einstein's theories and pushing the limits of our imagination. This sense of possibility leads us directly to another profound concept emerging from the same theoretical framework that gives us black holes, the idea of wormholes. Imagine if the vast distances of space, which take light years to cross, could be traversed in mere moments. Wormholes, often depicted in science fiction, are theoretical bridges or tunnels through the fabric of space-time itself, potentially connecting two distant points in the universe, or even, some speculate, different universes altogether. Think of it like this: if you wanted to get from one side of a piece of paper to another, you could walk across its surface. But what if you could fold the paper and punch a hole through it, instantly connecting the 2 points? That's the simplest way to visualize what a wormhole might do for space-time. While they remain purely hypothetical, a fascinating consequence of Einstein's theory of general relativity is that it mathematically allows for the existence of these cosmic shortcuts. Just as his equations didn't explicitly forbid black holes before their observation, they don't explicitly forbid wormholes either. The challenge is that for a wormhole to be stable and traversable, meaning something could actually pass through it, perhaps even a spaceship, it would require exotic matter. This isn't just unusual matter, but matter with negative energy density, something we've never observed or created in any significant quantity. This exotic matter would essentially act to prop open the wormhole, preventing it from collapsing in on itself the moment it forms. Without it, any wormhole that might theoretically appear would be infinitesimally small and collapse almost instantly, making it utterly useless for travel. So, could wormholes be the ultimate interstellar highways, offering a way to bypass the slow crawl of light-speed travel and reach distant galaxies in the blink of an eye? Or are they merely elegant mathematical curiosities, a playful quirk of the equations that has no bearing on physical reality? These questions push the very boundaries of physics. The answer, if it exists, likely lies in the uncharted territories where Einstein's general relativity, which describes the large-scale structure of the universe, meets quantum mechanics, which governs the incredibly small world of particles. For wormholes to truly exist and be stable, a unified theory of quantum gravity is probably needed, a grand theory that could reconcile these two powerful but currently incompatible pillars of modern physics. It's in this elusive realm that the true nature of space and time and the possibility of cosmic shortcuts might finally be unveiled. Beyond the mind-bending possibilities of wormholes, our cosmic journey takes us to an even more pervasive and profound mystery: dark matter. Imagine an invisible, undetectable substance that permeates the universe, making up an astonishing 27% of its total mass and energy. We can't see it, we can't touch it, and it doesn't interact with light or other electromagnetic forces, which is why it remains cloaked in darkness. Yet, its presence is undeniable due to its immense gravitational pull. This mysterious substance acts like an unseen cosmic scaffolding, shaping the very structure of galaxies and galaxy clusters. Without the gravitational influence of dark matter, galaxies would simply fly apart, unable to hold together their billions of stars. It's the silent architect of the cosmos, dictating the dance of celestial bodies on a grand scale. Scientists first inferred the existence of dark matter decades ago, when they observed that galaxies were spinning too fast to be held together by their visible matter alone. The stars on the outer edges of galaxies were moving at speeds that defied the laws of physics if only visible matter was accounted for. There had to be a hidden source of gravity, an invisible mass pulling everything together. This led to the groundbreaking hypothesis of dark matter, a substance that explained these gravitational anomalies. Over time, further observations, such as gravitational lensing, where the gravity of massive objects bends light from distant sources, provided even more compelling evidence for dark matter's existence. The way light bends around galaxy clusters suggests far more mass than can be seen, reinforcing the idea of a vast, unseen component. The quest to understand dark matter is one of the most pressing challenges in modern physics. Researchers around the world are employing various strategies to uncover its true nature. Some are building incredibly sensitive detectors deep underground, hoping to catch a rare interaction between a dark matter particle and ordinary matter. These underground laboratories, shielded from cosmic rays and other interference, are designed to detect the faint signature of what are known as weakly interacting massive particles, or WIMP, which are theorized candidates for dark matter. Other experiments are looking for indirect signs of dark matter, such as gamma rays or neutrinos that might be produced when dark matter particles annihilate each other in dense regions of space, like the center of our Milky Way galaxy. The Large Hadron Collider, the world's most powerful particle accelerator, is also part of this search, attempting to create dark matter particles in high-energy collisions, though so far without direct success. Unraveling the mystery of dark matter would not only revolutionize our understanding of the universe's composition and evolution, but it could also fundamentally alter our grasp of space and time themselves. If dark matter is made up of entirely new types of particles, it would open up a whole new sector of physics beyond the standard model, which describes all the known particles and forces. This would have profound implications for our understanding of fundamental forces and the very fabric of reality. Imagine discovering a new form of matter that interacts with gravity in ways we're only beginning to comprehend. Such a discovery could pave the way for completely new theories of gravity and potentially even offer insights into the nature of dark energy, the even more mysterious force responsible for the accelerating expansion of the universe. The implications are staggering, promising to reshape our cosmic perspective in ways we can barely imagine. While dark matter shapes the universe we see, an even more perplexing enigma is at play: dark energy. This invisible force is not merely holding galaxies together, it's actively pushing them apart, causing the universe to expand at an ever-increasing rate. Imagine throwing a ball into the air, expecting it to slow down due to gravity. Now picture that ball suddenly accelerating upwards faster and faster, defying all your expectations. That's essentially what dark energy is doing to the cosmos. It challenges our fundamental understanding of gravity, the very force that governs the attraction between all objects in the universe. Our current models suggest that gravity should be slowing the universe's expansion, but dark energy flips that idea on its head. The discovery of dark energy in the late 1990s was a colossal shock to the scientific community. Astronomers studying distant supernovae, which are incredibly bright exploding stars, expected to see the expansion of the universe slowing down over time. Instead, they found the opposite: the expansion was accelerating. These supernovae act as cosmic mile markers, their brightness allowing us to calculate their distance and the rate at which the universe has expanded since their light began its journey to us. The data from these celestial beacons pointed unequivocally to a repulsive force, something driving galaxies away from each other with increasing speed. This unexpected finding launched a new era in cosmology, forcing scientists to rethink everything they thought they knew about the universe's ultimate fate. So, what exactly is dark energy? The leading hypothesis suggests it might be a property of space itself, an intrinsic energy embedded within the fabric of spacetime. As space expands, more space is created, and with it, more dark energy, leading to an even faster expansion. Think of it like a continually inflating balloon where the inflation energy grows with the balloon's surface area. Another compelling idea is that dark energy could be a new kind of fundamental field, similar to the Higgs field that gives particles mass, or perhaps even a modification to Einstein's theory of general relativity on cosmic scales. Some theories even propose a dynamic form of dark energy that changes over time, potentially leading to different fates for the universe, such as a big rip where the expansion tears everything apart, or a big crunch if it were to reverse. These are not just abstract ideas, they directly influence how we imagine the past, present, and future of the entire cosmos. The quest to understand dark energy is even more challenging than the search for dark matter because it doesn't seem to interact with anything much at all, except on the grandest cosmic scales. We can't build detectors to find it in a lab, and we can't observe its direct effects within our solar system. Instead, scientists rely on large-scale astronomical surveys, mapping millions of galaxies to meticulously measure the expansion history of the universe. Projects like the Dark Energy Survey and upcoming missions like the Nancy Grace Roman Space Telescope are designed to gather even more precise data on how dark energy behaves over cosmic time. By studying the distribution of galaxies and galaxy clusters, and by observing countless supernovae, they hope to discern the subtle signatures of dark energy and distinguish between competing theoretical models. The answer to what dark energy truly is could redefine the very boundaries of physics, offering a comprehensive understanding of the universe's destiny. While dark energy reshapes our understanding of the universe's expansion, there's another mind-bending concept that challenges our everyday perception of reality: time dilation. This isn't just science fiction. It's a fundamental consequence of Albert Einstein's theories of relativity, which tell us that time isn't a constant, universal tick-tock, but rather a flexible dimension that changes depending on how fast you're moving and how strong the gravitational field around you is. Imagine for a moment two identical clocks. You keep one on your wrist here on Earth, while the other is taken aboard the International Space Station, orbiting our planet at incredible speeds. When the astronaut returns, even after months in space, their clock will show a tiny, almost imperceptible difference compared to yours. It will have ticked slightly slower. And it's not just the clock. The astronaut themselves will have aged a minuscule amount, less than if they had stayed on Earth. This isn't a defect in the clock or an illusion. It's a real, measurable effect that has been proven time and again with incredibly precise atomic clocks. The faster you move through space, the slower you move through time, and the stronger the gravity you experience, the more time slows down for you relative to someone in a weaker gravitational field. This concept of time dilation forces us to completely rethink our intuitive understanding of time as a steady, unyielding progression. It means that everyone experiences time differently, depending on their unique journey through space-time. The implications of this are profound, extending far beyond simply knowing that astronauts age a tiny bit slower. It means that for travelers zipping across the cosmos at near light speed, centuries could pass on Earth while only a few years pass for them. Picture yourself embarking on a journey to a distant star system. If you could travel fast enough, what might be a 1,000-year round trip for those you leave behind on Earth could feel like mere decades for you on your spacecraft. This isn't just about cosmic travel, though. Even here on Earth, the Global Positioning System, or GPS, relies on precisely accounting for time dilation. The satellites orbiting Earth experience weaker gravity and move at high speeds, causing their clocks to tick at a slightly different rate than receivers on the ground. Without correcting for these tiny relativistic effects, which amount to just microseconds per day, your GPS device would quickly become wildly inaccurate, throwing off navigation by miles. Now, if time dilation is noticeable at the speeds of orbiting satellites, what happens when we consider extreme gravitational environments, like those around a black hole? These cosmic behemoths are regions where gravity is so incredibly strong that nothing, not even light, can escape their pull. As you approach the event horizon, the point of no return around a black hole, time would slow down dramatically for you relative to an observer far away. For someone watching from a safe distance, it would appear as if you were moving in slow motion, gradually freezing in time as you drew closer to the event horizon. If you could somehow survive the immense gravitational forces and peer into a black hole, time would practically grind to a halt. This profound distortion of time near black holes is one of the most mind-bending predictions of general relativity, pushing the boundaries of what we consider possible. It highlights how utterly different reality can be when you step outside our familiar, everyday experiences, demonstrating that our perception of a consistent, universal march of time is merely a local approximation, applicable only within our relatively gentle corner of the cosmos. This radical understanding of time raises an even more fascinating and perhaps unsettling question. If time can be so flexible, could we ever travel through it? This brings us face to face with one of the most enduring mysteries and mind-bending concepts in theoretical physics, the grandfather paradox. Imagine for a moment that time travel into the past were possible. What if you journeyed back in time and inadvertently prevented your own grandparents from meeting? The very act of your existence would then be impossible, creating a catastrophic logical contradiction. If you were never born, how could you have traveled back in time in the first place to prevent their meeting? This isn't just a fun thought experiment from science fiction. It highlights a deep philosophical and scientific challenge to the idea of manipulating the past. The grandfather paradox isn't about the mechanics of building a time machine. It's about the very nature of causality, the unbreakable chain of cause and effect that governs our universe. If you could change the past, would the future simply rewrite itself, or would the fabric of reality itself unravel? Scientists and philosophers have grappled with this paradox for decades, proposing various fascinating solutions to resolve such logical inconsistencies. One popular idea, stemming from the many worlds interpretation of quantum mechanics, suggests that if you were to travel back and alter an event, you wouldn't change your own past. Instead, your actions would simply splinter off, creating a new, parallel universe where that altered timeline unfolds. In this scenario, you wouldn't erase yourself from existence. You would just be in a different universe, one where your grandparents perhaps never met, while the original timeline where you were born continues undisturbed in its own separate reality. This elegant solution allows for time travel without violating the laws of causality within any single universe. Another line of reasoning argues that time travel might be possible, but the universe self-corrects, making it impossible to genuinely change the past. Any attempt to alter an event would somehow be nullified, perhaps by an unforeseen consequence or an unlikely series of events that ensure the original outcome still happens. Think of it as destiny, but on a cosmic scale where the past is immutable and any intervention only leads back to the preordained course of events. However, many physicists remain skeptical, proposing that the grandfather paradox and others like it indicate that backward time travel is simply impossible. They argue that the laws of physics, as we currently understand them, fundamentally prohibit such journeys. Some theories suggest that while moving forward through time is a natural consequence of the universe's expansion, the arrow of time only points in one direction. The very structure of space-time might be designed to prevent causal loops, ensuring that effects always follow their causes. This perspective often aligns with the idea that the universe is inherently consistent and self-regulating, meaning that any physical mechanism allowing access to the past would inherently be blocked or prevented by the cosmos itself. The debate surrounding time travel and whether the grandfather paradox can be resolved or if it simply proves time travel's impossibility continues to fuel groundbreaking research and theoretical exploration. It pushes us to consider not just how time works, but why it works the way it does, forcing us to confront the deepest mysteries about the universe's fundamental laws and perhaps our place within them. While the grand paradoxes of time travel continue to challenge our understanding, another equally mind-bending phenomenon in the quantum realm offers a different kind of mystery, one that hints at connections far beyond our everyday experience: quantum entanglement. Albert Einstein himself famously dubbed this spooky action at a distance, and for good reason. Imagine two particles, perhaps two electrons, that are linked together in such a way that no matter how far apart they are, whether across a laboratory or across the entire galaxy, measuring the state of one instantly tells you the state of the other. If one electron is spinning clockwise, its entangled partner, even light years away, will instantaneously be found spinning counterclockwise, and vice versa. There's no time delay, no signal traveling between them. The connection is immediate, as if they are somehow still part of the same entity, defying the classical laws of physics that dictate nothing can travel faster than the speed of light. This isn't just theory, it's a phenomenon that has been repeatedly proven in countless experiments. This instantaneous connection raises profound questions about the very nature of reality and space-time. Could entanglement be a fundamental thread woven into the fabric of the cosmos, hinting at a deeper, more interconnected universe than we can currently perceive? Some researchers wonder if this spooky link could offer clues about potential avenues for faster-than-light communication, or even, in the most ambitious of theoretical leaps, a way to manipulate time itself. While direct communication or time manipulation through entanglement remains firmly in the realm of speculation and science fiction, the mere existence of such a phenomenon forces us to reconsider what we truly know about distance, information, and causality. It suggests that perhaps the universe isn't as separate and fragmented as it appears on the surface, but rather a seamless tapestry where everything is subtly, yet profoundly, connected. The implications of quantum entanglement are truly staggering, leading us to ponder whether the quantum realm holds answers that could revolutionize our understanding of space and time. It's a realm where particles can exist in multiple states simultaneously, where observation changes reality, and where information seems to flow without any regard for the speed limit of light. If our universe operates on these fundamental quantum principles, what other mysteries might be waiting to be uncovered? Could the rules that govern the very small also provide insights into the grand cosmic scale, unveiling shortcuts or connections that classical physics simply doesn't recognize? The ongoing exploration of entanglement pushes the boundaries of our knowledge, inviting us to imagine possibilities that once seemed utterly impossible, reminding us that the deepest secrets of reality might be hidden in the most unexpected places. While quantum entanglement hints at an interconnectedness within our universe, an even more expansive concept challenges our understanding of reality: the multiverse theory. Imagine not just one universe, but an infinite number of them, each one a separate cosmic bubble, some perhaps subtly different from our own, others vastly alien. This idea, once purely the stuff of science fiction, has gained traction in theoretical physics as a potential solution to some of the most profound puzzles in cosmology. If we are just one small part of an endless cosmic tapestry, It completely reshapes how we view our place in existence. One fascinating interpretation of the multiverse, often linked to quantum mechanics, proposes that every decision, every random quantum event, could branch off and create a new universe. Think about it, a seemingly minor choice you made this morning, like deciding between coffee and tea, might have split reality into two distinct universes. In one, you're sipping your coffee right now, and in another, a parallel you is enjoying tea. This isn't just about big, life-altering decisions. It's about every single possibility playing out across an endless array of parallel realities. It's a dizzying thought, suggesting that every path not taken in our lives is being lived out by another version of ourselves in a neighboring universe. Another perspective on the multiverse comes from inflationary cosmology, which suggests that our universe is just one of many bubble universes that continuously inflate and expand from a larger, ever-growing parent universe. Picture an infinitely vast ocean, and each bubble floating within it is an entire universe, complete with its own stars, galaxies, and perhaps even its own fundamental laws of physics. In some of these universes, gravity might be weaker, light might travel at a different speed, or the very elements that make up atoms might not exist. This concept is particularly intriguing because it could explain why our universe seems so finely tuned for life. If there are countless universes, it's not surprising that at least one of them would have precisely the right conditions for planets, stars, and ultimately, complex life to emerge. Then there's the idea of an infinite number of parallel realities, not just branching off from quantum events, but existing eternally side by side, each with its own unique history and future. In some of these, our world might be identical down to the last atom, while in others, subtle differences accumulate, leading to vastly different outcomes. Perhaps there's a universe where dinosaurs never went extinct, or one where humanity developed entirely different technological paths. If this is true, then every possible scenario you could ever imagine has already happened, is happening, or will happen somewhere in the vast expanse of the multiverse. It means that the possibilities aren't just limitless, they are all simultaneously real, existing in different cosmic pockets. The implications of a multiverse are truly staggering. It challenges the very notion of uniqueness and purpose. If there are infinite versions of you living out every conceivable life path, does that diminish the significance of your own choices? Or does it perhaps expand the meaning of existence, suggesting that the universe is far richer and more complex than we ever imagined? The search for evidence of these other universes is one of the most exciting and challenging frontiers in modern physics, pushing the boundaries of what we consider observable and testable. It forces us to reconsider the very definition of reality itself, inviting us to imagine a cosmos far grander and more mysterious than the one we currently inhabit. This leads us to perhaps the most monumental event in cosmic history, the Big Bang, often described as the beginning of everything. Picture an infinitely small, infinitely hot, and infinitely dense point, a singularity that contained all the matter and energy that would ever become our universe. Then, in an instant, approximately 13.8 billion years ago, this point exploded outward. But it wasn't an explosion in space as we typically imagine it. Rather, it was an expansion of space itself. Think about that for a moment. Space didn't just contain the explosion, it was created by it. And along with space, time also came into being. This revolutionary idea fundamentally reshapes our understanding of existence, moving beyond the notion of a universe that always was to one with a definitive origin. It's a mind-bending concept that challenges our intuition about the very fabric of reality. Yet, even as the Big Bang theory provides a compelling framework for the universe's evolution, it simultaneously opens up a cascade of profound questions that continue to challenge physicists and philosophers alike. What caused this initial explosion? What triggered the singularity to expand? Was there some external force, or was it an inherent property of this unimaginably dense point? These aren't easy questions, and current scientific models struggle to provide definitive answers. It's like trying to understand the ignition without knowing anything about the fuel or the spark. The Big Bang Theory describes the cosmic aftermath, but the true genesis remains shrouded in mystery, pushing our intellectual boundaries to their very limits. Perhaps the most perplexing question of all is about what, if anything, existed before the Big Bang. If space and time were created in this event, then the concept of before loses its conventional meaning. Can there be a before time began? This is where the ideas of physics and metaphysics truly converge. Some theories propose that our universe might be part of an endless cycle of big bangs and big crunches, a cosmic accordion continually expanding and contracting. Others suggest a multiverse scenario where our Big Bang was simply one instigation among countless others, each giving birth to a new universe. Every hypothesis attempts to grapple with the seemingly unanswerable question of origin, compelling us to consider whether the very concept of time had a starting point, or if it is an eternal, fundamental aspect of existence that simply manifested in our universe in a particular way. This takes us far beyond our current empirical reach and into the realm of pure theoretical speculation, forcing us to redefine our understanding of beginnings. While the past of our universe presents profound puzzles, its future is equally enigmatic, leading us to contemplate what many refer to as the end of the universe. This isn't just about whether the stars will burn out or galaxies will drift apart. It's about the very fabric of existence and whether time itself has an expiration date. The ultimate fate of our cosmos largely hinges on a cosmic tug of war between two powerful, unseen forces, dark energy and gravity. Imagine a rubber band stretched between two opposing magnets, one pulling outward with immense force and the other trying to snap it back together. On one side of this cosmic struggle is dark energy, the mysterious force believed to be responsible for the accelerating expansion of the universe. If dark energy continues to dominate, our universe could face a chilling end known as the Big Freeze, or more dramatically, heat death. Picture this: galaxies would continue to drift further and further apart, their light eventually becoming so diluted that the night sky would become an impenetrable black. Stars would exhaust their fuel, black holes would slowly evaporate through Hawking radiation, and the universe would eventually reach a state of maximum entropy, a uniform, cold, and empty void where no energy differences exist to power any kind of process. In this scenario, time wouldn't necessarily stop, but it would lose all meaning as nothing would ever change, nothing would ever happen. It's a truly chilling prospect, the universe fading out not with a bang, but with an endless, silent whimper. However, there's another possibility, an opposing force at play: gravity. If gravity were to somehow gain the upper hand over dark energy, the universe's expansion could slow, halt, and then reverse. This catastrophic event is known as the Big Crunch. Imagine the universe like a massive cosmic balloon, expanding for billions of years, then suddenly beginning to deflate, shrinking ever faster until all matter and energy collapse back into an infinitely dense, incredibly hot singularity, much like the one from which it began. This would effectively be the Big Bang in reverse, a cosmic implosion. In such a scenario, space and time would likely cease to exist as we understand them, collapsing along with everything else. The very concept of time would reach its ultimate conclusion, looping back to the initial state, perhaps even setting the stage for a new Big Bang, and thus a new cycle of existence, though we cannot say if such a cycle would be inevitable. The determining factor in this cosmic drama lies in the precise balance between these two forces, a balance researchers are still striving to measure with ultimate precision. The density of matter and energy, the strength of dark energy, and even the curvature of space all play critical roles in shaping the future trajectory of the universe. Our current observations lean towards the big freeze, but the universe has surprised us before. These are not mere academic debates. They touch upon the very nature of existence, prompting us to consider whether our time in this universe is merely a fleeting moment in an infinite expansion or part of a grander cyclical cosmic dance. While the ultimate fate of the universe remains a subject of intense scientific inquiry, another fascinating cosmic concept emerges from the complex equations of general relativity, the white hole. If black holes are cosmic vacuum cleaners, relentlessly pulling everything inward, then white holes are their theoretical opposites, continuously spewing out matter and energy into the cosmos. Imagine a celestial geyser endlessly erupting with light and particles, a place from which nothing can ever enter. It's a captivating thought experiment, one that challenges our understanding of gravitational physics and the very nature of spacetime. Unlike black holes, which we have observed and studied extensively, white holes remain purely hypothetical. They are mathematical solutions to Einstein's field equations, much like black holes themselves were once theoretical. However, to date, no observational evidence supports their existence. This absence of empirical data makes them one of the most intriguing, unproven phenomena in astrophysics, sparking debates and fueling the imaginations of scientists and science fiction writers alike. If they do exist, white holes could drastically alter our cosmic models, introducing new dynamics to the universe's evolution. They might represent a fundamental asymmetry in the universe, where processes don't always operate symmetrically in reverse. One of the most mind-bending possibilities associated with white holes is their potential connection to wormholes. Picture a wormhole as a shortcut through spacetime, a cosmic tunnel linking two distant points in the universe. Some theories suggest that a white hole could be the exit point of such a wormhole, with a black hole serving as the entrance. This concept, often explored in science fiction, proposes a cosmic highway system, allowing instantaneous travel across vast intergalactic distances. While exciting, this idea comes with immense theoretical hurdles, including the need for exotic matter with negative energy density to keep the wormhole stable and open. The sheer implications of such a connection are staggering, suggesting that the universe might be far more interconnected and navigable than we currently comprehend. Another speculative idea is that white holes could be the remnant of a big bang in another universe, or even a new kind of singularity resulting from a black hole's eventual decay. Think about it. If a black hole evaporates over an unimaginably long period through Hawking radiation, what happens at its final moments? Could it transition into a white hole, effectively reversing its cosmic role and becoming a source rather than a sink? This cyclical model would suggest a universe that is constantly recycling its matter and energy, with black holes transforming into white holes, perhaps even seeding new universes. While highly speculative, these ideas push the boundaries of what we consider possible, forcing us to re-evaluate our assumptions about the birth, evolution, and death of cosmic structures. Ultimately, whether white holes are real cosmic entities or simply elegant mathematical curiosities, they serve as a powerful reminder of how much we still have to learn about the universe. They highlight the vast unexplored territories within physics and astronomy, inviting us to ponder the deepest mysteries of spacetime, gravity, and the fundamental laws that govern existence. They force us to ask, What other hidden concepts lie within the equations of general relativity, waiting to be discovered or proven? The possibilities are as vast and enigmatic as the cosmos itself. Beyond the enigmatic dance of black and white holes, another incredibly ambitious theory attempts to unravel the universe's deepest secrets. This is string theory, a concept so profound it could fundamentally change how we view reality. Imagine for a moment that the smallest, most fundamental building blocks of our universe are not tiny, indivisible particles, but rather minuscule, vibrating strings of energy. Think of a guitar string. Depending on how it vibrates, it produces different musical notes. In string theory, these unimaginably small strings vibrate in different ways to produce all the various particles we know of, from electrons and quarks to photons and neutrinos. Each particle, then, is simply a different note played by these cosmic strings. This elegant idea suggests a profound underlying unity to everything we observe, from the smallest atom to the largest galaxy. One of the most captivating aspects of string theory is its potential to address one of the greatest challenges in modern physics: unifying quantum mechanics and general relativity. Quantum mechanics describes the universe at its smallest scales, governing the bizarre behavior of particles, while general relativity explains gravity and the large-scale structure of the cosmos. These two pillars of modern physics work incredibly well in their respective domains, but they fundamentally clash when attempts are made to combine them, especially in extreme environments like the singularity of a black hole or the Big Bang. String theory, with its vision of vibrating strings, offers a promising framework to bridge this divide, providing a single, coherent description of all forces and particles in the universe. If it succeeds, it could unlock answers to long-standing mysteries, such as the true nature of gravity and the very origin of our universe. But the implications of string theory don't stop there. To make its equations mathematically consistent, the theory requires the existence of more dimensions than the four we currently perceive: the three spatial dimensions and time. While our everyday experience is limited to these familiar dimensions, string theory suggests there could be as many as 10 or 11 dimensions in total. The reason we don't encounter these extra dimensions is thought to be because they are compactified or curled up into incredibly tiny spaces, too small for us to detect directly. Picture a garden hose viewed from a distance. It looks like a one-dimensional line, but up close, you can see its two-dimensional surface. Similarly, these extra dimensions could be curled up on scales far smaller than even individual atoms, making them imperceptible to our current instruments. This idea opens up mind-boggling possibilities, from parallel universes to entirely new ways for gravity to operate. However, despite its elegance and mathematical consistency, string theory faces a significant hurdle. It remains largely unproven by experimental evidence. Unlike other scientific theories that can be tested and verified through observation and experiment, the scale at which strings are thought to exist is incredibly small, far beyond the reach of even the most powerful particle accelerators we have today, like the Large Hadron Collider. This lack of empirical verification leads to a crucial question: is string theory true science, or is it simply a beautiful and complex piece of mathematics? While it provides a compelling framework for understanding the universe, its predictions are currently untestable, leaving many in the scientific community debating its ultimate validity. Some argue that without testable predictions, it cannot be considered a scientific theory in the traditional sense, while others believe that its internal consistency and ability to solve long-standing problems make it too compelling to ignore, even if direct evidence is elusive for now. Beyond the mathematical elegance of string theory, another concept pushes the boundaries of our understanding of reality, stretching our minds even further. This is the holographic principle, a truly mind-bending idea that suggests our seemingly three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface. Think of it like this: when you watch a three-dimensional movie or look at a three-dimensional image on your phone, the depth and volume you perceive are actually created from information displayed on a flat, two-dimensional screen. The holographic principle posits a similar but far grander scenario for our entire cosmos. It proposes that all the complexity and detail we experience in our three spatial dimensions, along with time, could be fundamentally described by information residing on a distant two-dimensional boundary, like a cosmic event horizon. The core of this idea stems from concepts developed in black hole physics, specifically the realization that the entropy, or information content, of a black hole is proportional not to its volume, but to the surface area of its event horizon. This was a profound discovery because it challenged the conventional understanding that information should scale with volume. If a black hole, an object with immense gravitational pull and information-absorbing properties, stores information on its two-dimensional surface, what if the entire universe operates on a similar principle? This radical notion suggests that our perception of depth, space, and even ourselves could be an elaborate illusion, a cosmic hologram rendered from distant data. It's a bit like living inside a video game where all the immersive three-dimensional graphics are ultimately generated from computer code stored on a flat drive. The implications of the holographic principle are truly staggering. If our universe is indeed a hologram, it could offer a fresh perspective on the nature of reality, space, and time. It might explain why certain physical laws appear to be precisely balanced, or why there are deep connections between gravity and quantum mechanics that currently elude us. This principle suggests that the fundamental building blocks of our reality might not be particles in three dimensions, but rather bits of information existing on a two-dimensional screen at the edge of the universe. This doesn't mean our experiences are not real, but it redefines what real means. It suggests that the reality we inhabit is a rich, detailed projection, similar to how a movie image seems real on screen, even though it originates from a flat film reel. However, just like string theory, the holographic principle faces significant challenges when it comes to experimental verification. How do you test whether the entire universe is a hologram? The scales involved are so immense, and the information encoded on this hypothetical two-dimensional surface is so subtle that direct observation is currently impossible with our technology. While there are some theoretical models, like the anti-de Sitter/conformal field theory correspondence, which provide mathematical evidence for holographic relationships in certain simplified universes, extending these to our own complex cosmos remains a monumental task. This leads to intense debates within the scientific community. Can we truly consider such a concept scientific if it remains purely theoretical? Or does its profound potential to unify disparate areas of physics warrant serious consideration, even without immediate empirical proof? The holographic principle forces us to question the very fabric of existence and pushes the boundaries of what we thought was possible, inviting us to ponder whether the universe we experience is truly as it appears, or if there's a deeper, more profound truth lurking beneath the surface, waiting to be unveiled. While the holographic principle challenges our perception of space, another fascinating concept called time crystals stretches our understanding of time itself. Imagine a typical crystal like a diamond or a snowflake. Its atoms are arranged in a precise, repeating pattern in space. That's a spatial crystal. Now, picture something similar, but instead of repeating in space, it repeats in time. This is the essence of a time crystal. Unlike anything we previously thought possible, these aren't just theoretical constructs. Scientists have actually created them in laboratories. The peculiar thing about time crystals is that they display a stable, repeating oscillation that occurs without any external energy input. It's like a clock that ticks forever, powered by nothing and defying the second law of thermodynamics, which states that systems tend towards disorder. This unique property means time crystals literally break time translation symmetry. In simpler terms, the laws of physics are usually the same at all times. If you perform an experiment today or tomorrow, the results should be identical, assuming all other conditions are the same. Time crystals, however, introduce a preferred direction or rhythm in time, much like a spatial crystal's atoms prefer specific locations in space. This continuous, self-sustaining oscillation, without relying on outside energy, challenges our most fundamental assumptions about how systems behave and evolve over time. It's a bit like finding a perpetual motion machine in the quantum realm, though the energy output is zero. This doesn't mean we can build a time machine, at least not in the sense of traveling through different eras. Instead, it reveals a new and exotic state of matter where time itself becomes a canvas for repeating patterns, much like space does for ordinary matter. The implications of discovering time crystals are truly profound. For one, they could revolutionize quantum computing. Traditional computers rely on bits that are either 0 or 1. Quantum computers use qubits, which can be 0, 1, or both simultaneously, allowing for exponentially more complex calculations. Time crystals, with their inherent stability and resistance to external interference, could provide a more robust and error-resistant platform for quantum information storage and processing. Imagine building quantum computers that are not only incredibly powerful but also inherently stable, capable of performing calculations without succumbing to the delicate quantum decoherence that plagues current design. Beyond computing, these strange structures might even lead to breakthroughs in highly sensitive sensors or extremely precise timekeeping devices. The very existence of time crystals opens up a new realm of possibilities for manipulating and understanding the fundamental properties of matter and time at the quantum level. The discovery of time crystals compels us to ask a much larger question. What other undiscovered phases of matter might exist in the cosmos? For centuries, we've primarily focused on the familiar states: solid, liquid, gas, and plasma. But as our understanding of quantum mechanics deepens, and as we push the boundaries of extreme conditions in laboratories or observe the universe's most exotic phenomena, we continue to uncover new and unexpected phases. Consider Bose-Einstein condensates, where atoms are cooled to near absolute zero and behave like a single, giant quantum wave, or superconductivity and superfluidity, where materials lose all electrical resistance or flow without any friction. These have transformed technology from medical imaging to high-speed trains. Time crystals are just the latest example of matter behaving in ways we never imagined. This continuous unveiling of new physical states suggests the universe is far richer and more complex than we've ever conceived, hinting at a vast, unexplored landscape of possibilities, each with its own unique properties and potential applications. The exploration of time crystals and other exotic states of matter brings us face to face with one of the most perplexing questions in all of science, the Fermi paradox. This paradox asks quite simply, if the universe is so vast, filled with billions of galaxies, each containing billions of stars, and many of those stars likely host planets capable of sustaining life, then where is everybody? Why, despite decades of searching, have we found no definitive evidence of alien civilizations? It's a profound silence that echoes across the cosmos, challenging our assumptions about life, intelligence, and our unique place within the universe. Consider the sheer scale. Our own Milky Way galaxy alone is estimated to contain up to 400 billion stars. If even a tiny fraction of these stars have planets in their habitable zones, capable of supporting liquid water and a stable environment, the numbers quickly become staggering. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. Given these immense probabilities, it seems almost inevitable that life, and even intelligent life, should have arisen countless times. Yet here we are, listening to static, with no clear signs of interstellar communications, megastructures, or any other telltale evidence of advanced civilizations. This absence of evidence is what makes the paradox so unnerving. It's not just a lack of discovery, but a glaring contradiction between high probability and observed reality. One of the most unsettling possible explanations for this cosmic quiet is what's often called the Great Filter. This theory suggests that there's some insurmountable barrier or series of challenges that prevents life from reaching an advanced interstellar stage. This filter could be in our past, meaning that the emergence of complex, intelligent life is extraordinarily rare, perhaps a 1 in a trillion event like the accidental formation of self-replicating molecules on early Earth, or the development of eukaryotic cells. If this is the case, then humanity might be incredibly unique, perhaps even alone in the universe, a fragile anomaly against an otherwise barren backdrop. This perspective, while perhaps comforting in its assertion of human specialness, also carries a profound sense of isolation. Alternatively, the Great Filter could lie in our future. This is a far more sobering thought, implying that there's some catastrophic hurdle that advanced civilizations inevitably encounter and fail to overcome. This could manifest in many ways: self-destruction through technological hubris, such as nuclear war or environmental collapse, the unintended consequences of advanced artificial intelligence, or perhaps even an existential threat that we haven't yet conceived, like a universal biological plague or a cosmological event that wipes out life on a grand scale. If the filter is ahead of us, then the silence of the universe isn't a sign of our uniqueness, but rather a chilling premonition of a fate that awaits all civilizations, including our own, once they reach a certain level of technological development. The absence of others then becomes a warning. There are also explanations that are less dramatic but equally thought-provoking. Perhaps advanced civilizations exist, but they are simply too far away for us to detect, operating on timescales incomprehensible to our brief existence. Or maybe they have evolved beyond the need for physical structures and interstellar travel, existing in forms or dimensions we can't perceive with our current technology. Some propose that they might be intentionally hiding, adhering to a prime directive that prevents interference with developing civilizations like ours, allowing us to evolve naturally without external influence. This idea of a galactic zoo or a cosmic quarantine zone is fascinating, suggesting we are being observed rather than ignored. The very act of contemplating the Fermi paradox forces us to re-evaluate our definitions of intelligence, progress, and survival, compelling us to consider humanity's place in the grand cosmic narrative from a profoundly different perspective. The silence isn't just an absence of sound. It's a profound mystery that invites us to look inward as much as outward. This leads us to another truly mind-bending possibility. What if the cosmic quiet isn't due to distance, filters, or prime directives, but because nothing out there is actually real? What if we are not alone, but simply unaware that we are part of a vastly intricate computer program? This is the core idea behind the simulation theory, a concept that has steadily gained traction among some leading scientists and philosophers. It proposes that the entire universe, with all its galaxies, stars, planets, and indeed all of us, could be an advanced computer simulation, meticulously crafted by a higher intelligence or a future civilization. It's a thought experiment that challenges our very understanding of existence. Imagine for a moment that our reality is like a video game, but on an unimaginably grand scale, infinitely more complex and immersive than anything we could ever design. In this scenario, the fundamental laws of physics that govern everything from the smallest subatomic particles to the largest superclusters of galaxies are not inherent properties of an objective reality, but rather lines of code, programmed rules within a gigantic cosmic algorithm. Every star that shines, every quantum fluctuation, every thought you have, could be a meticulously calculated output of this underlying simulation. This perspective offers a radical reinterpretation of everything we consider to be real, transforming the universe from a vast physical expanse into a colossal data stream. One of the most compelling arguments for simulation theory rests on something called the fine-tuning of the universe. When scientists look at the fundamental constants of physics, things like the strength of gravity, the mass of an electron, or the speed of light, they find that these values are incredibly precise. If even one of these constants were slightly different, life as we know it, or even the formation of stable atoms, would be impossible. It's as if the universe was tailor-made for life. From a simulationist perspective, this exquisite balance isn't a miraculous coincidence, but simply the result of careful programming. The parameters were set just right, allowing for the emergence of complexity, consciousness, and perhaps eventually other intelligent beings to run their own simulations within ours. However, this theory also opens a Pandora's box of profound questions and challenges. If we are in a simulation, who are the simulators? Are they beings of flesh and blood, or advanced artificial intelligences from a distant future? What are their motives for running such a complex program? Are we an experiment, a historical reenactment, or simply a form of entertainment? And what does it mean for our free will if our reality is nothing more than sophisticated code? Some argue that if we can simulate complex worlds ourselves, and we are getting better at it, then it's statistically likely that at least one of these simulated realities, perhaps even our own, would reach a point where it could also run simulations, creating an almost infinite nested hierarchy of simulated universes. Yet, despite its intriguing nature, simulation theory remains a deeply speculative concept. Critics argue that it's essentially unfalsifiable. There's no clear experiment we can perform right now to definitively prove or disprove it. Any glitch we might observe could simply be dismissed as an unknown physical phenomenon, or even a deliberate feature of the simulation itself. The idea also raises questions about what constitutes reality anyway. If our simulated experiences are indistinguishable from what we define as real, does the distinction even matter? Whether it's a plausible scientific hypothesis or simply a modern myth, the concept of a simulated universe forces us to confront our deepest assumptions about the nature of existence and our place within it. It transforms the grand silence of the Fermi paradox from a mystery of absence to a question about the very fabric of our being, asking if the answers to our cosmic loneliness might lie not in finding others, but in understanding the true nature of our own reality. Yet, even if our reality turns out to be a computer program, the universe still holds an abundance of tangible, awe-inspiring mysteries that defy simple explanation. Among the most extreme and fascinating are neutron stars. Picture this: the core of a massive star, several times larger than our Sun, collapses under its own immense gravity after a supernova explosion. What remains is an object so incredibly dense that a mere teaspoon of its material would weigh billions of tons. To put that in perspective, imagine taking every car, truck, and train on Earth and compressing them into a grain of sand. That's the kind of density we are talking about. These stellar remnants are essentially cosmic laboratories, where matter is squeezed to limits unimaginable anywhere else in the universe. The gravitational forces are so intense that they overcome the electron degeneracy pressure that normally keeps atoms from collapsing, forcing protons and electrons to merge into neutrons. This bizarre state of matter, a kind of nuclear superfluid, behaves in ways that are impossible to replicate or even truly comprehend on Earth. The surface of a neutron star is likely a solid crust of heavy elements under immense pressure, while its interior might contain exotic phases of matter like superfluid neutrons and even stranger, theoretical particles called quarks. Studying these enigmatic objects isn't just about satisfying our curiosity, it is about pushing the boundaries of our understanding of physics itself. By observing their extreme conditions, scientists can test the limits of our theories about gravity, nuclear forces, and the very fabric of space-time, uncovering secrets that could reshape our view of the cosmos. While neutron stars offer a glimpse into matter under unimaginable pressure, the universe also communicates through even more subtle and profound phenomena. Imagine space-time itself, the very fabric of our universe, not as a static backdrop but as a dynamic, flexible entity. Just as a heavy ball placed on a stretched rubber sheet causes a dip, massive cosmic events can create ripples in this cosmic fabric, much like tossing a pebble into a pond. These ripples are what we call gravitational waves, and their detection marked a revolutionary moment in astronomy. For centuries, our understanding of the universe relied almost entirely on light, radio waves, X-rays, and other forms of electromagnetic radiation, essentially what we could see with various types of telescopes. But gravitational waves are different. They are generated by incredibly energetic and violent events, such as the collision of two black holes, the merger of neutron stars, or the explosive death of massive stars. In 2015, after decades of theoretical prediction and painstaking scientific effort, the LIGO experiment, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves. This monumental discovery confirmed a key prediction of Albert Einstein's general theory of relativity and opened up an entirely new window into the universe. Instead of capturing photons, we were now effectively listening to the universe, picking up the faint tremors of spacetime itself. This allows us to observe phenomena that are completely invisible to traditional telescopes because they either don't emit much light or their light is obscured by dust and gas. For example, when two black holes spiral inward and finally merge, they produce a colossal burst of gravitational waves, but emit virtually no electromagnetic radiation. Gravitational wave astronomy is still in its infancy, but it promises to unveil a hidden universe, revealing cosmic symphonies of events we could never before perceive. It's like discovering a new sense, allowing us to delve into the most extreme corners of the cosmos and witness events unfolding in ways we never thought possible. Gravitational waves have opened up a new chapter in understanding the universe, but one of the most profound mysteries still revolves around something we experience every second of our lives: time itself. We all sense time moving forward, an unyielding progression from past to future. But why does time only flow in one direction? This concept is often referred to as the arrow of time. Think about it physically, many laws of nature are symmetrical. A movie played backward might look strange, but the individual interactions, like two billiard balls colliding, would still adhere to the laws of physics. Yet we never see a broken glass reassemble itself, or smoke retreat back into a cigarette. This irreversible progression is deeply linked to the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time, or at best remain constant. In simpler terms, everything tends towards disorder. A neat room naturally becomes messy over time, not the other way around. This principle explains why we age, why stars burn out, and why the universe is constantly expanding and cooling. The universe began in a highly ordered state, at least relative to its current vastness, and it's been becoming increasingly disordered ever since. This increasing disorder is what seems to give time its direction, marking the flow from a less probable, more ordered past to a more probable, disordered future. However, simply stating that entropy increases doesn't fully answer why time has an arrow. It merely describes what we observe. Why was the universe born in such a low entropy, highly ordered state to begin with? This initial condition, the Big Bang, seems to be the ultimate starting point for the arrow of time we experience. Some theories suggest that if the universe had begun differently, perhaps with higher initial entropy, time might not have had a discernible direction, or it might have flowed differently. Other, more speculative ideas delve into the quantum realm, proposing that the arrow of time could be an emergent property of quantum entanglement, or even related to the act of observation itself. The idea that consciousness or observation might play a role in how we perceive time's direction touches on some of the most mind-bending aspects of quantum mechanics, where particles seem to exist in multiple states simultaneously until observed. While these quantum explanations are fascinating, they are still very much at the forefront of theoretical physics and raise more questions than answers. The fundamental question persists: if the underlying laws of physics don't distinguish between past and future, why do we experience such a strong, undeniable arrow of time? The answer remains elusive, a profound puzzle that hints at deeper connections between the incredibly large scale of the cosmos and the incredibly small scale of quantum reality. Understanding the arrow of time and the universe's origin takes us directly to one of the biggest unsolved mysteries in physics, the quest for a theory of quantum gravity. This isn't just an abstract academic pursuit. It's about trying to fit together the two giants of modern physics, quantum mechanics, which describes the universe at its smallest scales, and general relativity, which explains gravity and the universe at its largest scales. These two incredibly successful theories, which have each been proven right countless times in their respective domains, simply do not work together. When you try to apply quantum mechanics to something as massive and gravitationally intense as a black hole, or to the very first moments of the Big Bang, the equations break down. They give us nonsensical answers like infinities. Imagine you have two meticulously crafted maps. One is incredibly detailed for a tiny garden, showing every leaf and ant, while the other maps entire continents, showing mountains and oceans. Both are perfect for their intended purpose, but you can't simply stitch them together and expect a seamless global map. That's a bit like the situation with quantum mechanics and general relativity. Quantum mechanics tells us that everything at the subatomic level is fuzzy, probabilistic, and discrete, meaning energy and matter come in tiny, indivisible packets called quanta. General relativity, on the other hand, describes gravity as the smooth curvature of space-time caused by mass and energy. When gravity gets extremely strong, like in a black hole's core or the mind-bogglingly dense conditions of the early universe, these two descriptions clash. We need a new map, a unified theory that can accurately describe gravity at the quantum level. What happens when space and time themselves are no longer smooth and continuous, but instead become lumpy and quantum? This is the realm of quantum gravity, a theory that hopes to bridge this fundamental divide. So, what are physicists doing to untangle this immense puzzle? Many ambitious theories are being explored, each with its own fascinating approach. One of the most well-known is string theory. This radical idea proposes that the fundamental building blocks of the universe aren't point-like particles at all, but rather tiny, vibrating one-dimensional strings. Different vibration patterns of these strings give rise to different particles, much like different notes on a violin string. What's truly revolutionary about string theory is that it naturally incorporates gravity into its framework, suggesting that gravity itself is carried by a specific type of vibrating string, often called a graviton. However, string theory comes with its own set of challenges, including the need for extra spatial dimensions beyond the three we experience, and the difficulty of directly testing its predictions. These extra dimensions are thought to be curled up so tightly that we can't observe them directly, but their presence would be crucial for the theory to work. Another prominent contender is loop quantum gravity. Instead of tiny strings, this theory suggests that space-time itself is not smooth and continuous, but is instead made up of discrete, interconnected loops. Imagine space-time as a fabric woven from incredibly fine threads. Loop quantum gravity proposes that these threads are tiny loops, and that the fabric of space-time has a fundamental pixel-like structure at the smallest scales. This approach leads to the idea that space and time are quantized, meaning there's a smallest possible unit of space and a smallest possible unit of time. This is a profound shift from our everyday experience of continuous space and time. While loop quantum gravity is very different from string theory, both strive to provide a quantum description of gravity and explain what happens in extreme environments where both quantum effects and gravitational effects are significant. The hope is that one of these theories, or perhaps a completely new idea, will finally provide the missing piece in our understanding of the cosmos, revealing the true nature of space, time, and everything in between. The implications of a successful theory of quantum gravity would be enormous, unlocking secrets about the universe's birth and the inner workings of black holes, and potentially giving us a deeper understanding of the very fabric of reality itself. Beyond the theoretical realms of quantum gravity and the universe's ultimate fabric, our gaze turns outward to the stars, to an astronomical frontier that is changing our understanding of life itself, exoplanets. For centuries, the idea of worlds orbiting distant suns was pure science fiction, a dream confined to the imaginations of astronomers and storytellers. Now, thanks to incredible advancements in telescope technology and clever detection methods, we live in an era where thousands of these alien worlds have been confirmed. This isn't just about finding dots in the sky, it's about uncovering entire planetary systems, each a potential stage for life to play out. The sheer number of discoveries is breathtaking. We've gone from speculating about a few possible planets to confirming more than 5,000 exoplanets, with thousands more awaiting confirmation. These worlds are incredibly diverse, ranging from gas giants far larger than Jupiter to rocky planets just a fraction of Earth's size. Some orbit their stars so closely that their surfaces are molten. Others are frozen in perpetual twilight, while still others are rogue planets, drifting alone through the cold vacuum of interstellar space, unattached to any star. Each new discovery adds another piece to the cosmic puzzle, challenging our preconceptions about what a planet can be and where life might arise. Perhaps the most thrilling aspect of exoplanet research is the search for worlds located within what astronomers call the Goldilocks zone, or the habitable zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right. On Earth, liquid water is absolutely essential for all known forms of life, acting as a universal solvent and facilitating countless chemical reactions. Finding a planet with the right temperature range is the first crucial step in identifying a potentially habitable world. Of course, being in the Goldilocks zone doesn't guarantee life, but it certainly tips the odds in favor. We're talking about worlds that might have oceans, weather patterns, and potentially even atmospheres similar to our own. The discovery of alien biospheres, if it ever happens, would be one of the most profound moments in human history. Imagine finding definitive proof of life on another planet, whether it's simple microbial forms or complex multicellular organisms. Such a revelation would redefine our place in the universe. It would force us to confront fundamental questions. Are we alone? Is life a common occurrence in the cosmos, bubbling up wherever conditions allow, or is it an incredibly rare cosmic accident? The implications would ripple through every aspect of our society, from philosophy and religion to science and culture. It would give us a new perspective on our own planet, highlighting both its fragility and its unique status as a cradle of life. Consider the ongoing efforts to not just find these planets, but to characterize them. Next-generation telescopes are being designed and built with the explicit goal of analyzing the atmospheres of exoplanets. By studying the light that passes through an exoplanet's atmosphere, scientists can identify its chemical composition. Detecting certain gases, like oxygen in combination with methane, could be a strong biosignature, a chemical fingerprint of life. Such a discovery would be far more compelling than simply finding a planet in the Goldilocks zone. It would move us from potentially habitable to potentially inhabited, a monumental leap. The James Webb Space Telescope, for instance, is already providing unprecedented insights into the atmospheres of some exoplanets, offering a tantalizing glimpse of what's to come. So, are we truly on the verge of finding another Earth, a twin world teeming with life, or is life rarer than we think? The answer remains elusive, a cosmic lottery waiting to be drawn. Every new exoplanet discovery brings us closer to understanding the true prevalence of planets capable of supporting life. But the leap from a potentially habitable world to an actually inhabited one is vast. It involves not just the right physical conditions, but also the complex, enigmatic process of abiogenesis, how life itself arises from non-living matter. This process, still largely a mystery on Earth, adds another layer of complexity to the search for extraterrestrial life. Regardless of whether we find complex civilizations or simple single-celled organisms, the search for life beyond Earth is fundamentally a quest for self-discovery, pushing the boundaries of our knowledge and our imagination. While we are busy searching for life on distant planets, an even grander cosmic mystery looms over us, one that profoundly influences not just our solar system, but our entire galactic neighborhood, the Great Attractor. Imagine an invisible, colossal force, so powerful it is pulling our Milky Way galaxy and thousands of other galaxies towards it, all at incredible speeds. This isn't just a gentle tug. We are talking about gravitational forces so immense that they are reshaping the very fabric of our local universe. Yet, despite its enormous influence, we cannot directly see what this great attractor actually is. It remains shrouded in mystery, hidden from our most powerful telescopes. The challenge lies in its location. The Great Attractor is situated in what astronomers call the zone of avoidance, a region of the sky obscured by the dense dust and gas within our own Milky Way galaxy. Our galaxy's spiral arms, packed with stars, nebulae, and cosmic dust, act like a thick veil, blocking the light from anything beyond it. It is like trying to see a distant city through a dense fog. You know something is there because of the light it emits, but you cannot make out any specific details. This cosmic camouflage has kept the true nature of the Great Attractor under wraps for decades, making it one of the most enigmatic gravitational anomalies in the cosmos. Scientists are essentially trying to map a hidden ocean current by observing the movement of ships on its surface without ever seeing the current itself. The evidence for the Great Attractor is compelling, even if its source is unseen. Astronomers have meticulously measured the movements of countless galaxies in our local universe, including our own Milky Way, and found that they are not moving randomly. Instead, they exhibit a coherent bulk flow, all streaming towards a particular region of space. This consistent directional motion cannot be explained by the expanding universe alone, nor by the gravitational pull of individual galaxies or known galactic clusters. It points to something far more massive, a gravitational anomaly so significant that it dominates the motion of a vast cosmic region, stretching hundreds of millions of light-years across. This observed large-scale motion is the primary clue, a gravitational fingerprint that hints at an unseen structure of immense proportions. The precise identity of the Great Attractor remains a subject of intense scientific debate and ongoing research. Some theories suggest it could be an enormous supercluster of galaxies, far larger and denser than any we have directly observed, perhaps a collection of galaxy clusters and filaments whose combined mass exerts this incredible pull. Another possibility is that it represents a vast concentration of dark matter, the mysterious, invisible substance that makes up about 27% of the universe's mass. Dark matter does not interact with light, making it inherently undetectable by traditional telescopes. If the Great Attractor is indeed a massive accumulation of dark matter, it would further deepen our understanding of this elusive cosmic component and its role in shaping the large-scale structure of the universe. Regardless of its exact composition, the sheer scale of the Great Attractor challenges our current cosmological models and forces us to reconsider the distribution of mass in the universe. It is a reminder that even in an age of advanced telescopes, vast swaths of the cosmos remain hidden, pushing the boundaries of what we can perceive and comprehend. While the Great Attractor pulls galaxies across billions of light-years, there exists an even more unsettling cosmic mystery, one that challenges the very foundation of our existence, the concept of vacuum decay. Imagine for a moment that our entire universe, with all its galaxies, stars, and planets, is currently existing in a kind of shaky, temporary state, like a ball resting precariously on a high ledge. Scientists propose that the universe might be in what is called a false vacuum. This means that the fundamental laws of physics as we know them, the very rules that govern everything from the smallest subatomic particles to the largest cosmic structures, might not be truly stable. They could be like a temporary setting on a grand cosmic dial, rather than the ultimate, most energy-efficient configuration. This idea of a false vacuum stems from quantum field theory, which describes how particles and forces interact. In this framework, the vacuum of space, far from being truly empty, is actually a bustling sea of fluctuating energy. The universe, according to this theory, naturally seeks the lowest possible energy state, much like a ball rolling down a hill until it reaches the bottom. If our universe is currently in a false vacuum, it means there is a lower energy state, a true vacuum that it could potentially transition into. the consequences of such a transition are almost beyond comprehension. If a quantum fluctuation, a random, unpredictable event at the subatomic level, were to occur, it could trigger a chain reaction. This tiny ripple in the fabric of reality could expand outwards at the speed of light, converting the entire universe into this new, lower energy state. The universe we recognize, the one governed by our familiar laws of physics, would cease to exist. This sudden and irreversible change, known as vacuum decay, would be the ultimate cosmic doomsday scenario. It would not be a slow, gradual cooling or a fiery expansion, but an instantaneous, catastrophic rewriting of reality itself. The very properties of matter would change. Electrons might behave differently, protons could become unstable, and atoms as we know them might simply cease to hold together. Stars would vanish, gravity might operate under different rules, and life as we understand it would be impossible. The expanding bubble of the true vacuum would sweep through the cosmos, transforming everything in its path. There would be no warning, no way to escape, and no remnants of our current reality would remain. It is a thought that sends shivers down the spine, a reminder of the fragility of our seemingly stable existence. Of course, it is crucial to emphasize that vacuum decay is a theoretical possibility, not an imminent threat. The conditions required for such an event are incredibly precise, and current calculations suggest that if our universe is indeed in a false vacuum, it is an extremely stable one, unlikely to decay for many, many billions of years, if ever. However, the mere existence of this concept highlights the profound questions that cosmology grapples with. It forces us to consider the incredibly delicate balance of fundamental constants that allow our universe to exist as it does, supporting stars, galaxies, and even life. It is a reminder that our understanding of reality is still evolving, and beneath the familiar surface of cosmic laws, there might lie deeper, more fundamental truths that could reshape everything we think we know. This deep mystery encourages us to look at the universe not just as a collection of objects to observe, but as a dynamic, quantum realm full of hidden possibilities, some of which are truly mind-bending. While vacuum decay offers a chilling vision of an abrupt end to reality, another thought experiment, even more mind-bending, challenges the very nature of our existence, the concept of Boltzmann brains. This idea springs from the same quantum fluctuations that underpin the notion of a false vacuum, but it pushes the implications of an infinite universe to their most extreme and unsettling conclusions. Imagine, if you will, a universe so vast, so eternally sprawling, that every conceivable arrangement of particles, no matter how improbable, is not just possible but inevitable. In such an unfathomably large and old universe, with an infinite amount of time and space for random events to occur, could order spontaneously rise from chaos, even if only fleetingly? The Boltzmann brain thought experiment suggests that in a universe of infinite extent and duration, the random jostling of atoms and energy could, purely by chance, momentarily assemble themselves into a self-aware entity, complete with memories, thoughts, and perceptions, a brain, in essence, floating in the void. This brain would flicker into existence in its most minimal form, just enough to be conscious, complete with a full set of false memories of a life lived, a world experienced, and a body possessed. It would then, presumably, dissipate back into the random energy from which it came, its existence no more than a momentary statistical anomaly. The chilling question then arises: if such random occurrences are possible, and indeed statistically more probable than the long, complex evolutionary process that led to our own brains, how can we be sure that we are not, in fact, Boltzmann brains? This bizarre notion forces us to confront some of the deepest philosophical questions about reality and consciousness. Are we truly the product of billions of years of cosmic evolution, intricate biological machinery housed within complex organisms on a vibrant planet? Or are we merely fleeting configurations of particles that have momentarily achieved self-awareness, our entire perceived reality an elaborate illusion? The Boltzmann brain hypothesis suggests that the vast majority of conscious observers in an infinite universe might not be the product of normal evolution within a structured environment like ours, but rather these solitary, disembodied brains that spontaneously pop into existence. This is why many physicists find the idea so unsettling. If Boltzmann brains are more likely to exist than our own type of evolved consciousness, it undermines the very foundation of our scientific observations and our understanding of the universe. Why should we trust our perceptions if they are statistically more likely to belong to a random, isolated brain than to a coherent, evolving observer? The implications are profound. If we are Boltzmann brains, then our memories of a past, our scientific understanding, and our very sense of being a part of a larger universe are all fabrications of our momentary, randomly generated consciousness. This isn't just an abstract philosophical game. It has serious consequences for how we interpret cosmological data and develop theories about the universe. If our universe were truly infinite and eternal in a certain way, the probability of Boltzmann brains arising would eventually dwarf the probability of evolved beings like us. This conundrum drives physicists to seek models of the universe that either limit its size or duration, or somehow suppress the formation of these spontaneous brains, ensuring that observers like us are the rule, not the extreme exception. It is a thought that underscores the incredible delicacy of our existence and how finely tuned the cosmos must be for our kind of consciousness to thrive, making this fundamental mystery of the universe a truly captivating and perplexing one. While the idea of spontaneous brains challenges our understanding of consciousness, other theoretical concepts push the boundaries of what is possible in the physical universe, particularly regarding space travel. For centuries, humanity has dreamed of traversing the stars, reaching distant galaxies, and exploring alien worlds. Science fiction has often been a powerful incubator for these dreams, giving us visions of journeys that defy the conventional laws of physics, none more iconic than the concept of warp speed. This revolutionary idea, popularized by countless movies and television shows, suggests a way to travel faster than light, not by breaking the cosmic speed limit, but by cleverly circumventing it. The most famous theoretical framework for this is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. His ingenious concept takes inspiration directly from Albert Einstein's theory of general relativity, which describes how mass and energy warp the fabric of space-time. Instead of trying to accelerate a spacecraft to faster than light speeds, which is impossible according to Einstein's equations, the Alcubierre drive proposes something far more elegant, expanding space-time behind the ship and contracting it in front. Imagine folding a long piece of paper so that two distant points are brought closer together. In essence, the Alcubierre drive would create a warp bubble around the spacecraft, allowing it to remain stationary within this localized bubble while the space-time itself moves, carrying the ship along with it. This means the ship itself wouldn't be moving faster than light through space, but rather space itself would be moving, creating the illusion of superluminal travel from an outside observer's perspective. It's a bit like being on a magic carpet that doesn't fly through the air, but rather the ground itself moves beneath it. This fascinating idea tantalizes scientists because, in theory, it doesn't violate Einstein's speed limit for objects moving through space, only for how space itself behaves. The implications of such a technology are truly mind-boggling. Interstellar travel, which currently seems like a generational, if not multi-generational, endeavor that would take thousands of years, could become a journey measured in days or weeks. Imagine visiting exoplanets within a human lifetime, exploring vibrant alien ecosystems, and uncovering the secrets of distant stars. The universe, which now feels impossibly vast and largely inaccessible, would suddenly shrink, opening up possibilities for exploration and discovery that were once confined to the realm of fantasy. This could transform our understanding of the cosmos, allowing us to directly observe phenomena and environments that are currently only accessible through the limited lens of telescopes and remote sensing. The Alcubierre drive, if ever realized, would fundamentally reshape our place in the universe and accelerate the pace of human progression in ways we can barely comprehend today. However, there's a significant catch, a hurdle so immense it currently makes the Alcubierre drive purely theoretical. The calculations for creating an Alcubierre warp bubble require something called exotic matter. This isn't just any regular matter. It's a hypothetical substance with negative mass or negative energy density. Think of it as matter that would produce a gravitational repulsion instead of attraction. We have no definitive evidence that such matter exists, let alone how to create or control it. Regular matter, with its positive energy density, would simply cause the space-time around the ship to curve inward, collapsing any potential warp bubble. The immense energy requirements are also staggering. Even for a small spacecraft, the amount of exotic matter and energy needed would be equivalent to many times the mass of the entire observable universe. This presents an enormous challenge that we are currently nowhere near overcoming. Despite these daunting obstacles, the theoretical framework developed by Alcubierre remains a beacon of hope for future interstellar voyages. It offers a tantalizing glimpse into a universe where humanity is not confined to its home planet, but is free to roam among the stars, prompting continuous research and imaginative thought experiments. Even with the tantalizing promise of warp speed, some of the universe's most profound mysteries remain stubbornly out of reach, often challenging the very foundations of our scientific understanding. One such enigma that has baffled physicists for decades is the information paradox. At its heart lies a fundamental conflict between two pillars of modern physics: Albert Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, the theory that governs the subatomic world. According to quantum mechanics, information cannot be truly destroyed. Every particle, every interaction, every bit of energy carries intrinsic data, and this data is preserved, even if it transforms into another form. Imagine burning a book. The book itself is gone, but the information it contained, now encoded in smoke, ash, and heat, theoretically persists. This principle, known as unitarity, is a cornerstone of quantum theory. However, black holes, the universe's ultimate cosmic vacuum cleaners, seem to defy this rule. General relativity tells us that anything that falls past a black hole's event horizon, the point of no return, is forever lost to our universe. It gets crushed into an infinitely dense singularity, and all the information about what it once was, its shape, its composition, its history, appears to vanish. If you were to throw a brick into a black hole and then a feather into another identical black hole, from the outside, they would look exactly the same. There would be no way to tell which black hole swallowed the brick and which swallowed the feather. This no-hair theorem suggests that black holes are characterized by only a few properties: mass, charge, and angular momentum, implying that any other information about the matter that formed them or fell into them is irrevocably erased. This direct contradiction with the quantum mechanical principle of information conservation creates the paradox. Then, things got even more complicated with the groundbreaking work of Stephen Hawking in the 1970s. He discovered that black holes aren't entirely black. They slowly evaporate over time by emitting a faint glow of particles now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where particle-antiparticle pairs spontaneously pop into existence. Sometimes one particle falls into the black hole while its twin escapes, carrying away a tiny bit of the black hole's energy, causing it to shrink. But here's the rub. If the black hole eventually evaporates completely, and the Hawking radiation it emits is purely thermal, meaning it doesn't carry any information about the matter that fell in, then the information paradox remains unresolved. Where did the information go? Did it simply disappear from existence, violating quantum mechanics? Or is it subtly encoded in the Hawking radiation in a way we don't yet understand? Scientists have proposed various solutions to this profound puzzle, each with mind-bending implications. Some suggest that information isn't truly lost but is somehow scrambled and encoded on the two-dimensional surface of the event horizon, like a cosmic hologram, before being gradually radiated away by Hawking radiation. This idea, known as the holographic principle, suggests that our three-dimensional universe might actually be a projection of information stored on a distant two-dimensional surface. Other theories posit that information might escape through baby universes, or that quantum gravity effects at the singularity somehow preserve it. The possibility that information truly is destroyed would necessitate a radical rethinking of quantum mechanics, a theory that has otherwise been incredibly successful in describing the world at its most fundamental level. The ongoing debate surrounding the information paradox is more than just an academic squabble among physicists. It strikes at the very heart of how we understand reality. Resolving this paradox could lead to a unified theory of quantum gravity, a single framework that reconciles general relativity and quantum mechanics, giving us a complete picture of the universe from its largest structures to its smallest particles. It could revolutionize our understanding of space-time itself, revealing hidden dimensions, parallel universes, or even the fundamental nature of existence. The implications would extend far beyond black holes, potentially reshaping our understanding of everything from the Big Bang to the ultimate fate of the cosmos. For now, the black hole information paradox remains a tantalizing mystery, a powerful reminder of how much we still have to learn about the universe's most extreme environments and the fundamental laws that govern them. Beyond the perplexing mysteries of black holes, our journey through the cosmic unknown also brings us face to face with an even grander question. What if the universe itself is part of an endless cycle, constantly being born, expanding, and then contracting, only to be reborn again? This concept, known as cyclic cosmology, offers a radical departure from the prevailing Big Bang theory, which suggests our universe began with a singular, explosive event approximately 13.8 billion years ago and will eventually end in a big freeze, a big rip, or a big crunch. Instead, cyclic models propose a universe without end, where time itself might be infinite, with each cosmic epoch representing just one chapter in an eternal story. Imagine for a moment that our Big Bang was not the genesis of everything, but rather a rebound from a previous universe that contracted back into an incredibly dense state. In this scenario, the universe undergoes a perpetual dance of expansion and contraction, like a cosmic accordion. Each cycle could last for trillions of years, with gravity eventually pulling everything back together, leading to a big crunch that then bounces back into a new Big Bang. This continuous process would mean that space and time, as we understand them, might not have a true beginning or end, but are instead an unending sequence of cosmic rebirths. It's a breathtaking thought, suggesting that every star, every galaxy, and perhaps even every life form is part of an ongoing, infinite cosmic drama. The implications are profound. If our universe is merely one in an infinite series, then everything that has happened, is happening, and will happen might repeat itself countless times over. Various theories of cyclic cosmology have been put forward, each attempting to address the theoretical challenges of bouncing from one universe to the next. Some models, for instance, involve extra dimensions or different types of exotic matter that facilitate the cosmic rebound, preventing a true singularity and allowing for a smooth transition from contraction to expansion. The appeal of these theories lies in their ability to potentially resolve some of the thorny issues presented by the standard Big Bang model, such as the initial conditions of the universe or the fine-tuning puzzle, which refers to the seemingly improbable precision of physical constants that allow for the existence of life. If there have been infinite universes before ours, then the probability of a universe with life-sustaining conditions arising becomes much higher, simply through sheer repetition. However, cyclic cosmology is not without its own set of significant challenges and unanswered questions. One major hurdle is the entropy problem. According to the second law of thermodynamics, the entropy, or disorder, of the universe must always increase over time. If the universe undergoes an infinite series of cycles, each bouncing from a big crunch to a big bang, then entropy should accumulate with each cycle, leading to an increasingly disordered and less energetic universe with every iteration. Eventually, after an infinite number of cycles, the universe should have reached a state of maximum entropy, a thermal equilibrium where no further changes are possible. This would mean that an infinitely old, endlessly cycling universe would effectively be dead, devoid of the complex structures like stars and galaxies that we observe. Overcoming this problem requires innovative theoretical solutions, such as mechanisms that reset or reduce entropy at the moment of the bounce, or even invoke multiverses where energy can be exchanged, creating pockets of lower entropy. Another crucial question is how the transition from contraction to expansion actually happens. What physical processes drive the bounce that prevents a true Big Crunch singularity and ignites a new Big Bang? This is where the realms of general relativity and quantum mechanics clash once more, just as they do with the black hole information paradox. A full understanding of the bounce mechanism would almost certainly require a theory of quantum gravity, a unified framework that can describe the universe at its most extreme densities and temperatures. Until such a theory is fully developed and experimentally verified, the precise physics of a cosmic rebound remains speculative. Yet, the possibility that our cosmos is merely one chapter in an eternal story, constantly being reborn from the ashes of its predecessors, pushes the boundaries of our imagination and compels us to consider the universe not as a singular event, but as an unending, dynamic process. This mind-bending idea of a constantly cycling universe leads us to another truly profound and unsettling concept, one that pushes the very boundaries of our understanding of existence: quantum immortality. This notion emerges from certain interpretations of quantum mechanics, particularly the many worlds interpretation, which proposes that every quantum measurement or event causes the universe to split into multiple parallel realities. In essence, for every decision you make, every choice the universe makes, or every random quantum fluctuation, a new reality branches off containing every possible outcome. If you choose to turn left, there's a universe where you turned left and another where you turned right. if a quantum particle decays, there's a universe where it decayed and another where it didn't. Now apply this to consciousness. If every possible outcome exists in its own distinct universe, what happens when you face a life-threatening situation? Imagine a scenario where you are in a car accident. In the classical sense, there are two outcomes: you survive or you don't. But in the many worlds interpretation, there would be a universe where you survived and one where you didn't. Quantum immortality suggests that your consciousness, from its subjective point of view, would always follow the path where you survive. You would simply cease to exist in the universes where you died, but your conscious experience would continue in a parallel universe where the accident played out differently and you lived. It's as if your conscious awareness always jumps to the timeline where it persists. This isn't about magical self-healing or defying physics within a single universe. Instead, it's about the persistence of subjective experience across an infinite number of parallel realities. From your perspective, if quantum immortality holds true, you would never experience your own death. Every near miss, every illness, every potentially fatal event would simply resolve in a way that allows your consciousness to continue, transferring to a universe where the favorable outcome occurred. This doesn't mean you're immune to pain or suffering. It just means that the final, permanent cessation of consciousness, the lights-out moment, could never be experienced from within your own subjective reality. The implications of quantum immortality are both fascinating and deeply unsettling. It challenges our most fundamental notions of life and death, suggesting that our personal existence might be far more resilient than we ever imagined. It blurs the line between science and philosophy, leaning heavily on the interpretation of quantum mechanics, which itself remains one of the most enigmatic areas of modern physics. This idea isn't universally accepted among physicists. Many find it highly speculative and untestable, firmly placing it in the realm of philosophical thought experiments rather than scientific fact. How would we ever prove or disprove such a theory? The very nature of parallel universes means they are unobservable from our own, making empirical verification incredibly difficult, if not impossible. Yet, despite its controversial nature, quantum immortality forces us to grapple with profound questions about the nature of consciousness itself. Is consciousness merely an emergent property of the brain, or is there something more fundamental to it that allows it to persist across branching realities? If our minds are indeed capable of such an endless journey through an infinite multiverse, then our understanding of what it means to be alive and what it means to die might be far more complex and intertwined with the very fabric of the cosmos than we could have ever conceived. It suggests a universe not just filled with infinite possibilities, but one where your personal story, from your own point of view, might truly be eternal, unfolding across an unimaginable landscape of parallel realities. This journey through the mind-bending possibilities of quantum reality and subjective persistence now leads us to another truly astonishing concept, one that, if proven real, would entirely reshape our understanding of time itself: tachyons. Imagine particles that don't just move fast, but move faster than the speed of light. Now, our current understanding, based on Einstein's theory of special relativity, tells us that nothing with mass can ever reach or exceed the speed of light. As an object accelerates, its mass increases, requiring infinite energy to get to the speed of light, making it an unbreakable cosmic speed limit. But what if there were particles that always moved faster than light? That's the idea behind tachyons. These hypothetical particles aren't just speeding bullets. Their very existence would turn our intuitive grasp of cause and effect upside down. In the bizarre world of relativity, if a particle moves faster than light, its behavior would appear to defy the normal flow of time. Specifically, if you were able to observe a tachyon from your perspective, it would appear to travel backward in time. Imagine throwing a ball, and instead of flying away from you, it appears to arrive in your hand before you even let go. That's the kind of mind-bending implication we're talking about. A tachyon emitted from point A might be detected at point B before it was ever emitted from point A, creating a paradox that would shatter our fundamental understanding of causality. If effects could precede their causes, the very structure of our universe and our ability to predict or understand events would collapse. The idea of a tachyon existing means that the future could influence the past rather than the other way around. Physicists have explored these theoretical constructs extensively, but despite decades of searching, no tachyon has ever been observed. They remain purely hypothetical, a fascinating mathematical quirk that emerges from the equations of relativity rather than an observed reality. Some have speculated that if tachyons do exist, they might be lurking in the quantum foam, that strange, fluctuating fabric of spacetime at the smallest scales, perhaps popping in and out of existence in ways we can't detect with our current instruments. Others suggest they might be related to exotic states of matter or energy that are beyond our present technological capabilities to measure. However, the prevailing scientific consensus leans towards them being a theoretical impossibility, a consequence of extending equations beyond their physically meaningful limits. Yet the idea persists, fueling the imaginations of scientists and science fiction writers alike. If tachyons were real, how would they interact with normal matter and energy? Would they carry information, allowing for impossible communication or even time travel in some form? The very notion of particles that could travel backward in time forces us to question whether our familiar, linear progression from past to present to future is the only way time truly behaves at the most fundamental level. It opens up a philosophical rabbit hole, asking whether causality is an immutable law of the universe or merely a consequence of our perceptions within our specific corner of spacetime. Are these elusive particles merely a mathematical curiosity, or are they a hint at a deeper, stranger reality that we have yet to fully comprehend? The search for them continues, though largely in the theoretical realm, pushing the boundaries of what we believe is possible within the cosmic framework. While the theoretical possibility of tachyons challenges our understanding of time, perhaps an even more tangible, yet equally baffling, mystery from the stars forces us to consider whether we are truly alone in the universe. Imagine, if you will, a warm summer night in 1977 at the Big Ear Radio Observatory in Ohio. For 72 seconds, a signal unlike any other flooded their receivers. It was so strong, so clear, and so precise a burst of radio waves at a frequency of 1,420 megahertz, a frequency specifically protected for astronomical purposes due to its significance. This frequency corresponds to the natural emission line of neutral hydrogen, the most abundant element in the universe, making it a prime candidate for any civilization attempting to signal their existence across the vast cosmic distances. The signal was so striking that one researcher, Jerry Amon, circled it on a printout and wrote, "Wow," next to it, a spontaneous exclamation that forever gave this event its name, the wow signal. This wasn't just random noise or terrestrial interference. The signal had characteristics that made it stand out dramatically. It was narrow band, meaning it occupied a very specific frequency range, much like a radio station, rather than the broad, noisy spectrum of natural cosmic phenomena. It also showed a clear rise and fall in intensity, consistent with what you might expect from a rotating source in space, potentially a distant planet or star system broadcasting towards us. And perhaps most compellingly, it matched the expected drift in frequency that a signal from beyond Earth would exhibit due to the Earth's rotation and the observatory's movement. All these factors combined to create a profound sense of intrigue and excitement among the scientists. Was this it? Was this finally the moment humanity received a message from an intelligent civilization across the cosmos? The immediate follow-up was intense. Astronomers pointed the Big Ear and other radio telescopes around the world back to the precise location in the constellation Sagittarius from which the signal originated. They listened and they listened again for hours, days, weeks, and even years, but the signal was never heard again. It simply vanished, leaving behind a tantalizing whisper of what might have been. This lack of repetition is precisely what makes the WOW signal so enigmatic. If it were truly an alien broadcast, you might expect it to be repeated, perhaps as a continuous beacon or as part of a more elaborate message. Its singular appearance makes it incredibly difficult to explain, ruling out many conventional astronomical explanations like pulsars or quasars, which tend to emit signals in a more regular, predictable fashion. Scientists have proposed numerous hypotheses over the decades. Could it have been an undetected passing satellite reflecting a signal? Unlikely, given the signal's characteristics and the protected frequency. What about a natural yet unexplained cosmic event? While the universe is full of bizarre phenomena, none have ever been observed to produce a narrow-band signal of this kind. Some even suggested an Earth-bound origin, perhaps a secret military transmission or an obscure form of radar, but careful investigation has consistently failed to find any terrestrial source that could account for its unique properties and fleeting nature. The fact that it has never been replicated, either naturally or artificially, leaves the WOW signal perched precariously between the known and the unknown, a persistent question mark in our quest to understand the universe. The enduring mystery of the WOW signal serves as a powerful reminder of how little we truly understand about the vastness around us. It pushes us to consider not just the scientific explanations, but also the philosophical implications. If it was indeed an extraterrestrial message, even an accidental one, what does that tell us about the possibility of life beyond Earth? And if it was just some incredibly rare, inexplicable cosmic anomaly, what other secrets might the universe hold that defy our current models and instruments? For over 4 decades, this 72-second burst of radio waves has fueled debates, inspired research, and ignited the imaginations of millions, remaining one of the most compelling and frustrating unresolved puzzles in humanity's search for intelligent life. From the event horizons of black holes where time itself might stretch and warp, to the baffling possibility of a multiverse, a cosmic expanse teeming with countless other universes, our journey through the boundaries of space and time has undeniably revealed a cosmos far stranger and more magnificent than any fiction we could ever imagine. Every single discovery, whether it is the detection of gravitational waves echoing from colliding black holes or the unexplained whispers of a signal like WOW, ceaselessly raises new, profound questions. It proves beyond a shadow of a doubt that the universe is not a static, fully understood entity, but a dynamic, ever-unfolding realm absolutely brimming with mysteries just waiting to be solved. As we continue to push the very limits of scientific inquiry, building more powerful telescopes, designing more sensitive detectors, and formulating more daring theories, we inch ever closer to truly understanding our minuscule yet significant place in the grand, intricate tapestry of existence. This endeavor is not merely about accumulating data, it is about expanding consciousness itself, challenging our preconceived notions, and daring to gaze into the seemingly unfathomable. The universe is an endless source of wonder, a perpetual invitation to explore and to question. So keep looking up, keep asking questions, and keep that sense of childlike awe alive. The next groundbreaking discovery, the next revelation about how everything works, could very well be just around the corner, waiting to reshape our understanding of reality once more.